Welcome dear children to today's session in physics. Today we are discussing some problems from capacitors. Capacitors, combination of capacitors, energy stored in capacitors. There are many conceptual questions being asked from capacitors. Today we won't be able to do means all the questions, but some questions we will do. Okay. So first question is to find the effective capacitance between A and B. So the diagram looks complex, but it is very simple actually. Between A and B, how many capacitors we have? 6 capacitors. Okay. Now you look. C2, C3 and C4. How are they connected actually? Actually, they are connected in series. C2, C3 and C4 are connected in series. This C1 end of C2 is connected to the other end of C3. One end of C3 is connected to C4. So C2, C3 and C4 are connected in series. Likewise, C6 and C5, they are connected in series. Then what about the two combination? That means the series combination of C2, C3, C4 and the series combination of C5 and C6 are in parallel. So two series combinations are in parallel. So when we draw the reduced diagram, it looks like this diagram. Okay, which diagram? This diagram. Okay, so many diagrams are there. They are reduced ones. So first the question, it reduces to this. As I said, C2, C3, C4 in series and C5 and C6 also in series, and both the series combinations in parallel. Okay, so if they are in series, so what will be the effective capacitance of this C2, C3, C4? You have to calculate using the equation 1 by CS is equal to 1 by 4 plus 1 by 2 plus 1 by 4. Doing the calculation, you will get it to be 1 microfarad. Okay, the series combination of 4, 2 and 4 microfarad, you will get the answer to be 1 microfarad. Likewise, the series combination of 4 and 2 microfarad, you will get it to be 4 by 3 microfarad. Okay, so this this diagram, it reduces to this one. Got it? So what we have, 1 microfarad and 4 by 3 microfarad are in parallel, and that parallel combination is connected in series with what? 4 microfarad. Got it? So that's what. Now again that diagram is reduced. 1 microfarad and 4 by 3 microfarad are connected in parallel. So effective capacitance of 1 microfarad and 4 by 3 microfarad connected in parallel, it is 7 by 3 microfarad. That's what this diagram shows. Okay, this diagram, that means 4 microfarad and 7 by 3 microfarad connected in series. Now you just find the effective of that. So you'll get it to be 28 by 19 microfarad. So that is the final answer to the question. Okay, so this is the way. So here we have shown like what with arrow mark. It's better if you draw one below the other. First you draw this one, this diagram. This is first one. Then below that you draw this diagram, second one, and below that this third diagram, and this is the fourth diagram. Like that you have to draw in the notebook and you can solve. So this is one method of solving this question. And if you want to write in detail, you can go in steps. So C2, C3, C4 are in series, their net capacitance. Got it? So in simple words you write, don't go for detailed steps. So you can calculate all the values like this and finally the answer. So this is how you should solve this type of question. So drawing reduced diagrams, as I explained earlier, it is very, very important. Okay, now next question also like this, effective capacitance, finding the effective capacitance between A and B. This diagram also looks very complex, but it is very simple. Okay, so let's start. So here between A and B, so here you consider this circuit. So what about the connection? 120 picofarad and 80 picofarad are connected in parallel. Okay, so they get added, so that effective will be 200. Likewise, here you look. Here 200 picofarad and 300 picofarad. This one. These two are connected in series. Likewise, 60 picofarad and 120 picofarad are connected in series. So this circuit reduces to the parallel combination of this series connection, okay, and this series connection, and the middle one, that is 140 picofarad. Got it? So when we draw the reduced diagram, so we are going to discuss the reduced diagram. Here we have the reduced diagram. So you look, it is redrawn. So in this diagram, here on in the previous diagram, that series combination of 200 and 300, it is replaced by that effective, and 60 and 120 replaced by its effective 40. Okay, likewise here one parallel combination was there, that is 120 and 80, it is replaced by its effective. So likewise it is replaced. Now we are going to reduce this diagram also. That means here you can see a parallel combination of 120, 140 and 40. So in the next step of the diagram, that means that parallel combination is replaced by its effective, that is 300. So in that diagram, 200, 300 and 600 comes in series. With that series combination, this 50 comes in parallel. That's what this is drawn. Okay, so that is this diagram. So 300 is here, then that is drawn. In the next diagram again, this series combination is replaced by its effective, that is 100. Okay, so in finding the effective capacitance, you can use those equations. I'm not showing the steps, I'm just explaining. So 200 plus, that means 1 by 200 plus 1 by 300 plus 1 by 600. When you do the simplification, you will get 100. So it becomes 300 in series with the parallel combination of 150. Okay. Then that parallel combination is in series with another 100. Now we move on to the next step. So it becomes 300, 150 and 100 in series. Okay, this 150 is that effective of that parallel combination. So we have 300 plus 150 plus 100. We'll get the effective capacitance to be 50 picofarad. So the final answer is 50 picofarad. I'm not showing the steps. The steps you have to write yourself. Okay. Now in this question, again, we have series and parallel combination. So in this question, you can see this 1 microfarad and 1 microfarad are connected in parallel, and this 4 and 4 are connected in parallel. Okay. So when we draw the reduced diagram, so in the next step, we are just drawing another form of the same diagram to show that exact parallel combination and how the capacitors are coming. Like that it is drawn. So here you look, here again we have this 1 microfarad and 1 microfarad in parallel. So effective of that becomes what? 2. Likewise 4 and 4, here also it is 4. So 4 and 4 will be connected in parallel, means 8. So 8 and 8, this is 8, here also 8 comes. So 8 and 8 will come in series. Here 2 and 2 will come in series. So the next diagram comes like this. That is, we have 2 and 2 in series. Okay. And 8 and 8 also in series. Got it? So when 2 and 2 are in series, we have what the effective capacitance to be 1, and 8 and 8 in series, 8 by 2, 4. So use that equation which we discussed. So here we have 8 and 8, so giving 4, 2 and 2 giving 1. So when 1 and 4 are connected in parallel, we have the final answer to be 5 microfarad. Okay, so I'm explaining only the reduced diagram steps you write. Now here we have an additional topic. This topic, it's not there in the syllabus, but based on this many years questions were asked. So we will just discuss. The concept is very simple, related to our topic. Okay, redistribution of charge, common potential. So that word common potential is very important. Okay, so what is the situation? When two capacitors, they are charged initially to different potential differences. So one is charged to some potential difference 50 volt, second one is charged to some potential difference say 25 volt, and they are connected to each other. So you can see in the diagram, you can see the two capacitors are connected, which are charged to different potential differences V1 and V2. They are connected together like this. So since the capacitors are of different capacitance and they are charged to different potential differences, you can see the values are different. Okay. So the thing is this, the charge stored on these capacitors will be different. So what happens when these capacitors are connected like this? The thing is this, they will share their charge. Till what value they will share their charge? So here it is written Q1 dash and Q2 dash, the charges. Now they share their charge so that their potentials become same. So it's not like since both means they share their charge till both of them acquire same charge, not like that. Till what time they share their charge, their potentials become same. See here the potentials were V1 and V2. After sharing, their potential become same. That's what we call as common potentials. So till the capacitor plates attain a common potential, they share their charges. That new charges after sharing we have written as Q1 dash and Q2 dash. So charges before sharing and charges after sharing will be different. Got it? On the two capacitors. But what is the case? They share their charges till they attain the same potential difference or the common potential. Got it? So till then they share their charges. So that's what. So now we will obtain an expression for this common potential. So how we obtain the expression for common potential? So we assume two capacitors of capacitances C1 and C2 charged to potentials V1 and V2, and the charges with them before sharing, that means before connecting, they will have charges like Q1 equal to C1 V1 and Q2 equal to C2 V2. Okay, now we are assuming the condition V2 to be greater than V1. So charge start transferring from the capacitor C2 to C1 till they attain a common potential V. So how will you find the common potential V? Common potential V is given by total charge by total capacitance. So here in what way the two capacitors are connected? The two capacitors are connected in parallel. So what will be the effective capacitance? C1 plus C2. Effective capacitance will be C1 plus C2. And we said before connecting the charges are Q1 and Q2, which is C1 V1 and C2 V2. So what is the total charge actually? C1 V1 plus C2 V2. So total charge is Q1 plus Q2, that is C1 V1 plus C2 V2, and the total capacitance is what? C1 plus C2. Okay, so what will be the common potential? C1 V1 plus C2 V2 divided by C1 plus C2. So this is the expression for common potential, and that is very important in solving problems. Okay, so Q dash and Q2, Q1 dash and Q2 dash will be the charges on the capacitor after sharing or after attaining common potential. So what it will be, Q1 dash will be equal to C1V and Q2 dash will be equal to C2V. Okay, and the thing is this, Q1 plus Q2 will be equal to Q1 dash plus Q2 dash, because total charge before sharing will be equal to total charge after sharing. That is to be maintained, the conservation of charge. Is that clear? Because here the capacitors are not connected to any source. Only the charged capacitors are connected together. So total charge before sharing will be equal to total charge after sharing. That means Q1 plus Q2 will be equal to Q1 dash plus Q2 dash. Okay, so that important equation in solving problems, many problems we see in previous year board questions. So we have to use this equation. Now, based on that logic, we have the problem. A 10 microfarad capacitor is charged by a 30 volt DC supply and then connected across an uncharged 50 microfarad capacitor. So here, first of all, both the capacitors are not charged. Only one capacitor is charged, that 10 microfarad capacitor. It is charged by 30 volt supply. So what will be the charge on the capacitor? We can find using the equation Q equal to CV. You are asked to find final potential difference across the combination and the initial and final energies. That means total energy before sharing and after sharing. How will you account for the difference in energy? We will find out. So first, how will we proceed? First, you need to find that common potential. That is what is asked as the first question. So just to substitute for C1 V1 plus C2 V2 by C1 plus C2, microfarad is to be converted to farad. Okay, so important point to be noted here is this, that is V1 equal to 30 volt and V2 is equal to 0, because that second capacitor is not connected to any source in the beginning. Okay, so we'll get the common potential to be 5 volt. Common potential is 5 volt. Now, the second part, we need to find initial and final energy stored. So you can use the equation half CV square. So initially energy is stored only in the first capacitor, because second capacitor is not connected to any source. So initial electrostatic energy is what, half C1 V1 square. So substituting, we'll have 4.5 into 10 raised to minus 3 joule. Okay, so that is the initial electrostatic energy. Now coming to the next step, that is final electrostatic energy. Final electrostatic energy, how will we get? It is for the combination. So when we take the combination, the expression becomes what? Half into CV square is the equation. That C becomes what? C1 plus C2. Okay, C becomes C1 plus C2. That is what? 10 plus 50. Okay, then V becomes what? That common potential 5. So our expression becomes half into C1 plus C2 into V square, where V is the common potential. So substituting, we will get 0.75 into 10 raised to minus 3 joules. So we got initial what energy stored? Initial energy stored was 4.5 into 10 raised to minus 3 joule. Now the final energy stored is 3.75 into 10 raised to minus 3 joule. Sorry, 0.75 into 10 raised to minus 3 joule. So what is the difference in energy? That difference in energy is 3.75 into 10 raised to minus 3 joule. Just to subtract. So what happens to that difference in energy? That energy is actually lost. It is lost in the form of heat and electromagnetic radiation as the charge flows from first capacitor to second capacitor. So when the two charged capacitors are connected together like this, there is loss of energy, and that loss of energy is in the form of heat and electromagnetic radiation. Okay, so this type of problem very important. Okay, but in the textbook it's not given as a example question it's given. Now we will discuss an example question, that is example 210. A 900 picofarad capacitor is charged by 100 volt battery. How much electrostatic energy is stored by the capacitor? That part is very easy. You can solve it using the equation half CV square. Second part, the capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. What is the electrostatic energy stored by the system? So, new electrostatic energy we have to find. So, energy stored by the capacitor before sharing is, as I said, half CV square will give you 4.5 into 10 raised to minus 6 joule. Now, when we share, that means when the capacitor is connected to another capacitor, uncharged one, then the thing is this, both the capacitors are of same capacitance. So, here sharing will take place till the common potential is achieved. Now, to find the total energy of the system, we are using the equation half QV. How we do, I will explain. So the thing is this, both the capacitors are of same capacitance. So when they share the charges, both the capacitors will have same charge. That is, if Q is the initial charge, final charge on both it will be Q by 2. Q dash will be equal to Q by 2. Common potential we assume to be V dash. So we have half, that is total energy of the system will be sum of the energy stored in both the capacitors. So it will be half Q dash V dash into 2. That means sum no. So both the same. So 2 into half Q dash V dash, that is Q dash V dash. Now what is V dash? V dash is Q dash by C. Okay, V dash is Q dash by C. So substituting, we have these steps from which we get half into half QV. So this half QV is nothing but the energy which is stored previously. That means before connecting, that means when the one capacitor was connected to the source, what was the energy stored? That is half QV. So half of that will be the total energy stored in the system. So total energy stored in the system will be 2.25 into 10 raised to minus 6 joules. So this is the steps given in textbook. Easy steps I will tell you, just try. That is, you can use the equation half CV square itself. That means before what disconnecting from the battery we already found. Here when you use that equation, that C should be effective capacitance of both, that means parallel combination. Okay, so C by 2 comes and V becomes what? Common potential. So you just find the common potential, you have the expression for common potential and you use the equation half CV square, where that C is the effective capacitance of that parallel combination and V is the common potential. So you will be getting the same answer. So that logic also you can apply here. Now we are discussing some questions from exercises, that is 9, 10 and 11. Question number 9. Explain what would happen if in the capacitor given in exercise 2.8 a 3 mm thick mica sheet of dielectric constant 6 were inserted between the plates. First one, while the voltage supply remained connected. Second one, after supply was disconnected. So what you have to find is what happens if the capacitor, that means if a mica sheet is inserted between the capacitor plates. Two different situations. First case, battery remains connected. Second case, battery is disconnected. So the reference is question number 8. In question number 8, under the given conditions, we found the capacitance of the capacitor. It was not with a dielectric, it was without dielectric, and we got it to be 1.77 into 10 raised to minus 9 coulomb. And here we rounded it to what? 1.8 into 10 raised to minus 9 coulomb. Okay, and it's given a mica sheet of what dielectric constant 6 is inserted. Now, here what point you have to keep in mind is this: voltage supply, if it remains connected, the potential difference between the capacitor plates remains the same. So this is a very important point. So if the battery is remaining connected, always the potential difference across the capacitor plates will be same. If it is disconnected, okay, as per the situations it will be changing. So here first case, battery remains connected means potential difference remains same. Now when the capacitor, that means when a dielectric is inserted between the capacitor plates, you know what happens to the capacitance? Capacitance becomes K times the initial capacitance. That means 6 into 1.8. So it will be 10.8 into 10 raised to minus 9. So you can change that unit. So we'll get 108 picofarad. So here it is changed to picofarad. So we have 108. Now the charge on the capacitor plates will be, the charge on the capacitor plates, how will you find charge on the capacitor plates? Q equal to CV. Just to substitute in that equation. So we'll have 1.08 into 10 raised to minus 8 coulomb. So that is the answer to the first part. Now the second part, after the supply is disconnected. When the supply is disconnected, charge on the capacitor plates remains the same. So that makes the difference between the two situations. When the supply is disconnected, charge on the capacitor plates remains same. If the battery remains connected, potential difference remains the same. Okay, so here since the supply is disconnected, charge on the capacitor plates remains same, and that is 1.8 into 10 raised to minus 9 coulomb. Here the effect of dielectric is the same on capacitance. Capacitance becomes K times the initial one. So 108 picofarad itself. Now what about the potential difference? You know, now the capacitance is C. Okay, and the charge is same. So what is V? The potential difference V is equal to what? Q by C. Q by C. Now what is Q now? Q is that Q0 itself. That is Q0 divided by, then what about C? C is KC0. Q C KC0 is C. So Q0 by C0, you know, Q0 by C0 is the potential difference V0. So this equation we can write as what? V0 by K. So what is the potential difference with the dielectric? Now it became V0 by K. So this is how we get this expression V0 by K. Very simple. V is Q by C, where Q is Q0 itself because charge remains the same. But C has changed. C is KC0. So KC0. So we have V0 by K. So substituting we will get 16.6 volt. So that is that question. Which one? Ninth one. Now coming to 10th question. Very direct one. 12 picofarad capacitor is connected to 50 volt battery. How much electrostatic energy is stored in the capacitor? Direct question it is. You can use the equation half CV square. You will get 1.5 into 10 raised to minus 8 joule. Now coming to 211. A 100 picofarad capacitor is charged by a 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in this process? So this is the problem which is similar to that problem of common potential and all. So we will discuss the solution. So first step is to find common potential. So here also the two capacitors are of same value. We'll get the common potential as 100 volt. Now you have to find initial energy stored. Since the second capacitor is not connected to the battery before sharing, so energy is stored only in one capacitor, that is first one. So initial energy stored is which one? Half C1 V1 square. So we get the answer. So the next step is to find what final energy stored. Final energy is stored in the system of two capacitors, the parallel combination of two capacitors. So final energy is equal to half C1 plus C2 into V square, where C1 plus C2 is the effective capacitance of parallel combination and V is the common potential. Substituting, we will get the answer 6 into 10 raised to minus 6 joule. So what about the lost energy lost? Energy lost is the difference. Initial energy minus final energy. You will get 6 into 10 raised to minus 6 joule. So that is the answer. And in what form it appears? It appears in the form of heat and electromagnetic radiations and is lost. It is lost in charging that second capacitor. So only this much for today. Thank you.